Welcome back everyone. In this lecture I will continue with the subgroups. Okay, so I will introduce some more subgroups that we can actually construct inside a group, and again all these constructions are very abstract constructions, so we will actually see some examples to demonstrate all these constructions. Okay, so let's fix some notation before starting. So as before, we take G to be a group. So now what we want to do, so we take some subset S of G. Okay. So now I want to talk about group generated by this subset. Okay. So what we want to do, we want to talk about the subgroup generated by this capital S. Okay. So first of all, what is the meaning of this? Let's actually think about it. So theoretically speaking, it is not that hard to define what is this group generated by S. Okay. So basically you look for all subgroups that containing S. Okay. So if you want some subgroup that is actually generated by S, then it should contain all possible multiplications of elements of S, inverses of S, and all combinations of that. Okay. But theoretically speaking, so that must be the smallest group with respect to the containment, and that contains S. Okay. So we recall a fact, and that fact actually guarantees given any subset S, you always have the subgroup generated by S. So what is that fact? It is about intersection of subgroups. Suppose you have a collection of subgroups inside G, call it H alpha. So this is the collection of subgroups of G. Okay. So then what we can do, we can talk about the intersection of all these subgroups. Okay. So what is this? It is those elements inside G such that this X should be in H alpha for all alpha in I. So now what we can prove, this is also a subgroup of G. So how do you prove? So recall that to prove something is a subgroup, it is enough to prove that you take two elements A B in that subset and you consider the product A B inverse, that should be again in that subset. That is what we verify. Okay. So let's try to verify that. You start with A B inside this intersection H alpha alpha in I. So what we want to prove? So we need to prove that AB inverse is also inside this intersection. Okay, this is one of the characterization of subgroups that we proved in the earlier class. So let's see why it is true. So since AB is actually inside in the intersection, you know that AB, both of them must be in H alpha for all alpha in I. Okay. So we have AB is in H alpha for all alpha in I, because both AB, they are elements of intersection of H alpha. So now if you think about it, H alphas are all subgroups that is given. So that means this implies AB inverse should be in H alpha for all alpha in I. Then this implies the product AB inverse must be in the intersection of H alpha alpha in I. Okay. So this is what we need to verify. So that is verified. So that means arbitrary intersection of subgroups must be subgroup. Okay. And it is not hard to see the union will never be actually. Unions need not be subgroups. Okay. So, you can take integers itself and then try to actually think about some counter example there. Okay. Now, how it actually helps us to actually construct the subgroup generated by S. So, let us see what we can do. So, we start with S being a subset of G. So, now what I can do? I can construct this collection. So, you take all possible subgroups of G such that S is contained in H. So, what is this? H is a subgroup of G and then S is contained in H. So, this collection must be non-empty because G is one such element. Okay. G is already in this collection. Call this collection A. Okay. So, now what I can do? I can actually just take intersection of all these subgroups. Okay. That is allowed. I can take all this H where H is coming from E. So, since this collection is non-empty, this intersection makes sense, and this intersection from the fact that we proved earlier becomes actually a subgroup. So, this is a subgroup of G. Note that since S is contained in H for all H in this A, so S is contained in H for all H in A. So, that would imply that this S is contained in this intersection. Okay. And we have one more property. If I take any other H dash which contains S and H dash is a subgroup of G, so then it is immediate that this intersection of H in A must be contained in H dash. Why? Because this implies H dash is inside this collection. Okay. So, this says this is actually the smallest group, this is the smallest. So, smallest means what? With respect to the inclusion, that smallest subgroup that contains S. Okay. So, it is meaningful to call this subgroup as subgroup generated by S. So, because you need all elements of S to get this subgroup. If you miss something, there is a chance that the subgroup may go down. Okay. The intersection may go down. Okay. This is somewhat theoretical way of understanding the subgroup generated by S. So, this actually guarantees that there exists the smallest subgroup that contains S. Okay. So, I say that it is actually the smallest. I will leave it to you to actually think about why it is unique. So, what I mean by that? So, you have to actually first write down what is the meaning of uniqueness here and what is the meaning of smallest. So, if you write down that, more or less it is easy. So, maybe let me do it. Suppose you have, let us say, H1, that is some subgroup containing S, and say it is smallest. Okay. So, let us say smallest subgroup containing capital S. Similarly, H2 is also smallest subgroup containing S. So, what is the meaning of that? S is contained in H1 and H2, and whenever there is another group H dash and you have another group H dash that contains S, then that should imply that H dash contains H1. So, that is the meaning of the smallest. Okay. So, now you can see that you can change the role play. So, if you use H2 in the place of H dash, then you can see that H2 contains H1 and similarly H1 contains H2, and then this would imply that H1 equal to H2. Okay. So, that is why it is the smaller subgroup that contains S. So, that is the smallest is possible, that is because intersection of subgroups must be subgroup. So, for example, you can take H1 intersection H2. So, that is again a subgroup that contained in both H1 and H2, and that also contains S. Okay. So, H1 H2 cannot be smaller than H1. In that case, then H1 intersection H2 becomes somewhat smaller, okay, with respect to the containment. So, that is why H1 should be equal to H1 intersection H2, and then which is same as H2. Okay. So, okay. So, here we are talking about actually somewhat there is a partial order, okay, and then with respect to that partial order. So, the partial order is defined on the set of all subgroups of G that contains S. Okay. The partial order is given by just set inclusion. So, in that partial order, with respect to that partial order set inclusion on this collection of subgroups of G that contains S, we are saying that you have unique minimal element. So, that unique minimal element you can call it minimum or the smallest. Okay. So, that is what we are doing. Okay. So, now let us try to understand more about this subgroup in a more practical way. For example, if I take some element A in A, okay. So, before that let us introduce one notation. So, here is the notation. So, because this subgroup generated by S, that is unique, we can denote it by just angled bracket S by the subgroup generated by capital S. Okay. So, now given this A in A, I can also talk about the subgroup generated by A. So, then in the earlier class I told this must be exactly same as A power k, k coming from integers. So, one thing to notice, the set on the right side it is a subgroup and it contains A, and obviously it is the smallest group contains A, because any other subgroup that contains A will contain all A power k, all the integral power of A. Okay. So, that is why this is the smallest. So, this is the smallest subgroup containing A, or this is the subgroup generated by A. So, now let us take, okay, for example, 2 elements and then see what happens. Okay. So, let us first look at some example, let us not get into the abstract thing. So, let us look at concrete example. Let us take Z plus. So, we know that it is a group. Okay. So, here we can talk about, for example, subgroup generated by some subset. Okay. So, let us take for example 2 and 3. Okay. So, then what will be the subgroup generated by 2 and 3? Okay. Let us look at what will be the possibility. So, we already know that any subgroup of Z must be of the form some n Z. Okay. So, it is enough to determine what is that n. So, let us write down this as n Z. Okay. But if you do not like this, maybe we can directly do it, that is also a problem. So, let us do it in 2 different ways. First, let us do using our result. So, you take subgroup generated by 2, 3, call it n Z. So, now what do you want to do? You want to determine the n. Okay. So, what is the property? So, this 2 is inside n Z. So, that means what? 2 can be written as n times some d1. So, that means n divides 2. Okay. Similarly, 3 is inside n Z, and that means n divides 3. So, n divides both 2 and 3, and n is now coming from, we can take it to be non-negative integer. Okay. Otherwise, we can replace by minus n, there is no issue. So, you have a non-negative integer and that actually divides both 2 and 3. it cannot be 0 because then NZ becomes 0. So 2, 3 are there. So n is non-zero and natural number that dividing 2 and 3. Because 2 and 3 are relatively prime, you can easily conclude that n must be 1. So that means this subgroup generated by 2, 3 must be just integers. Okay, let us look at this from the different point of view, just from arbitrarily group theory point of view. So we take this subgroup generated by 2, 3 and then see what are all the possible elements that it should have. So a moment thought will reveal that it should contain, okay, it should contain all possible integral combination of 2, 1, 3, okay. Why? Because first of all 2 is there. So any multiple of 2 which will be 2 plus 2 plus 2. So positive multiple must be there. Its inverse, the negative multiple must be there. Similarly multiple of 3 positive as well as negative must be there and their combination should be there. So the subgroup generated by 2, 3 must be containing all this. But you take this set on the right hand side. So then look at this. So this is 2n1 plus 3m1, okay, and then if you subtract with some 2n2 plus 3m2, so then see what you are getting. Then you can see that this is nothing but 2n1 minus m2 plus 3m1 minus m2. So this is again some multiple of 2 plus some multiple of 3. So integral linear combination of 2 and 3. So if I take A minus B, where AB is coming from this set, in this set, okay. So then you can see that this is A and this is B minus B, okay. If I take AB here and then A minus B is again inside this set. So that tells that this 2n plus 3m is already a subgroup. So because it is already a subgroup, this must be contained in this subgroup generated by 2, 3. That tells that the subgroup generated by 2, 3 must be of the form 2n plus 3m where nm are in Z. But you already know that since 2 and 3 are relatively prime, so there exists some n naught m naught such that 2n naught plus 3m naught equal to 1, okay. So 2n naught plus 3m naught equal to 1. So this subgroup must contain 1. So once I know that this must contain 1, so then all multiples of 1 must be there. So that means this should contain Z, okay. So then that means this subgroup generated by 2, 3 must be equal to Z, okay. So similarly you can actually try to play around and then see what will happen. So I leave one exercise. So this is something simple. Start with some A1 etc. AK from Z, and then if you are interested in the subgroup generated by AK, so then it has two description as before. So first of all it is some DZ, and then you can determine what is the D, okay. So first of all this must be equal to some N1 A1 plus etc. plus NK AK, all integral combination of this A1 etc. AK, where is N1 etc. NK, they are all integers. So this is the description of the subgroup, and you can also say that this is DZ and this D should be exactly equal to GCD of A1 etc. AK, okay. For example, this A1 etc. AK, so that lie inside DZ, okay. So this AI is inside DZ, so that imply that D divides AI, okay. So that will imply that D divides the GCD of A1 etc. AK. So now what we need to prove? So we need to prove that, so since D divides this, so this already tells you that, so if you call this as some D1, okay, so then the D1 is nothing but multiple of D. So that means D1 is inside DZ. Okay. So that means if I take D1Z, that should be contained in DZ. Okay. But you already know that, so the GCD can also be written as some integral combination of this A1 etc. AK. Okay. So if I take the GCD, so that is D1, which is GCD of A1 etc. AK. So then it can be written as there exist, okay, some M1 etc. MK such that this is A1 M1 plus etc. plus AK MK. So this is something you must have learned it in elementary number theory. Okay. So that implies that this D1 is indeed inside this set. Okay. Yeah. So now what we want to prove, so we already have that actually, yeah. So because yeah, because we already have D divides D1. So because D is D1 is the greatest common divisor. Sorry, this should be the other way. If D divides AI for all I, okay, so then this D1 should divide D. Okay. So let us take for example 2, 4. So then the GCD of that is just 2. Okay. So 2 divides, maybe this is not good example, let us take something bigger. So let us take 6 and 18. So then you can see that GCD is 6 because 6 divides both. Okay, suppose something divides, so 2 divides both 6 and 18, so that implies 2 divides 6. Okay, so what I wrote was correct. So D divides D1. Okay, now what we want to prove? We want to prove that D must be the GCD. Okay, so now D is already divides D1, so that is why we get that D1 is Z is contained in DZ. So now you can see that D1 is already combination of all these things. Okay, so now what we want to say? Yeah, D is the smallest greatest common divisor among all of them. Okay. Yeah. So you already know that D1 divides AI for all I. Okay. So in particularly, if you can write, if you can prove that these two are same, these two are same. So, that means D must be of the form some n1 a1 plus etc nk ak. So, then that would imply that D1 must divide D. Okay. So, that would imply D1 equal to D. Yeah, but it is not hard to prove these two are equal. So, the subgroup generated by A1 etc AK is same as all possible integral linear combination of A1 etc AK. Okay. So, now using the definition of GCD of A1 etc AK and this being the generator, you can simply verify that D must be the GCD of A1 etc AK. So, we have already done that. Okay. So, I will leave it you to check this is exactly same as this. Okay. So, now let us go back to the abstract group and then see what will happen if we consider the subgroup generated by any set S. Okay. So, just for simplicity, let us first take S being actually two elements. So, if S is singleton, then we already saw how the subgroup generated by that singleton A looks. Okay. If S is empty, then the subgroup generated by S must be identity, because that is the smallest group containing empty set. So, now let us look at two elements A comma B, and then I am interested in understanding what will be the subgroup generated by this. So, you can see that definitely. So, if you call this is H, okay. So, let us call it Hs. So, definitely all the integral powers of A must be there and all integral powers of B must be there, okay, for any K and K dash inside each. So, this must be there in that subgroup. So, now we can also take just product between them. Okay. You can take A power K, B power K dash. So, this is also should be inside your Hs. But note that these are not the only elements. Okay. The thing is, if you are working in general group, okay, which may not be commutative. So, in particularly AB may not be same as B. Okay, this can happen. For example, if you take a set of all invertible matrices, even 2 by 2 invertible matrices, it is not hard to find two elements such that the product of those two elements AB is not same as BA. Okay. So, that means this is there, but again this is also there. Okay. So, you have to consider all these possibilities, but are they all the elements? So, let us look at. So, Hs definitely contains elements of the form AK, BK dash and then some BL and then AL dash, where K is coming from Z. Okay, all of them. Let us write K dash, L dash, all of them are from Z. Okay. So, this is definitely contained in Hs. Okay. So, now whether these are all the only things, we can just try to verify. So, if you start with some word, okay, so this is basically what you are trying to do. You are abstractly trying to determine what are all the possible elements that can lie inside the subgroup generated by AB. Okay. So, you have to consider all possible words. Okay. So, the product of elements of G, they are called words. Okay. So, you have to consider all possible product of words that you can perform using AB. So, note that A is there, B is there, that implies A inverse is there, B inverse is there in Hs. So, now definitely you have to consider all the words that you can actually get using these 4 letters. For example, A, B, A, B, and then A inverse, B inverse, and so on, something like this. Okay. But if you think about it, so this also can be grouped as follows, like A and then B and then A square and then B and then A inverse, B inverse. Maybe let's stop with B inverse, then it becomes B square. So now, so this element that I constructed na, A, B, A, B, A inverse, B inverse, B inverse. So this is also there in the group. So this must be inside your inside your HS. Okay. So that means something like this, A B, A square B, A inverse B minus 2. So that is also inside your AS. So that means these are not the only type of elements that you can actually get. So you can also get something like this. Okay. So A power some K1, B power some K2, and then similarly you go like some A power K3 and B power some K4. Okay. So these are all the elements. These elements also must be there because A, B don't commute. So for example, something like this also should be there. But what's about again adding something more here, A power K5 and then B power K6. So this is also should be there, and then you can see that any finite string or finite word like this must be there inside HS. Okay. So that means, so for example, A cube B power minus 2, A B power 3 and then A power minus 2, B power minus 1. So this should be inside your HS. Okay. So since they don't commute, so this word must be included, there is no option. So this suggests that you take all possible things like this, A power B power K2 and then A power, okay, so what I call K3 B power K4 and so on. So now it may end with A, so where let us say some KR, or it may end with B also. Okay. So maybe the best way to actually write down this, we can write it as tuples A power K1 B power K2 and then A power M1, maybe I will put 1 on the top, 1 1 1 2 B power K2 2 and so on, A power K 1 some R B power K2 R. So now you allow all integral powers, some of them could be 0. So all these elements should be inside your HS. So then your HS, if you think about it, if you take words of the form and then if you take the inverse of that, you can see that, okay, this is just a simple exercise. So if I have a product of elements, let us say k elements inside G, so call it X. So then X inverse will be exactly equal to, you reverse the product AK inverse etc. A1 inverse. For example, AB inverse is B inverse A inverse. Okay. So this is your X inverse. So prove that this is the X inverse. Okay. With this exercise, you can see that if I take this X, then X inverse will be again B minus K2R, A power minus K1R and so on, B K12 and then minus B minus K11. Okay. So that means if I collect all the elements of this form, A K11, B K21 and so on, A K1R, B, K2R, where all these Kj's are coming from Z. This itself form a group, form a subgroup. And obviously it contains AB. So, this is the subgroup generated by AB. You can see that if you want to give this general description using only AB for elements of HS, you have to allow all these possibilities, okay, all the words. Obviously, there will be some relations, we will talk about relations later. If we use those relations, so we may actually end up getting very less elements. Okay, it can happen that it can become finite if you are in the finite group, but if when you think abstractly, you have to allow all possible words like this. So, I will leave it to you to think about what will happen if you take some finite set S, and then if you deal with that, if you call this S as some, let us say A1 etc. some AK, then you try to get description for this HS. Okay. So, basically you take this S and then S inverse, and then you take all possible words that you can form from those letters A1 etc. AK and A1 inverse etc. inverse, and then take possible products in any order, and that will be your HS. Okay. You will be able to prove that is actually the subgroup, smallest subgroup containing S. So, I will give very explicit description in the problem sheet, and then you can try to do it. Okay, I will stop here, we are running out of time. Thanks.